Hello everyone and welcome back. My name is Mr. Cobalt and today I'm going to be going over how to calculate the wavelengths of light given a certain transition of an electron in the hydrogen atom. So we're going to be using the equation, the Rydberg equation, or a rendition of the Rydberg equation to help us solve these problems. So the first problem is you have an electron that transitions from n equals 6 to principal energy level n equals 5. So then they're asking, what is the lambda or the wavelength of light that's emitted? So the first thing you want to do is you need to calculate the energy lost by the electron in this transition. So the change in energy of the electron. Or in another way of putting it, of the atom itself, because the electron is part of the atom. So, that delta E, so the delta E, the change in energy of the electron, is going to be equal to negative 2.18 times 10 to the negative 18 joules. And that's going to be multiplied by 1 over n, right? So n squared, and this is going to be the first n, right? So you're going to have n equals 5 and n equals 6. So the first one you have is 6. So that's going to be your n equals 2. So n from here to here minus 1 over n squared. So which one is which? So this is going to be negative. So the change, since we're going from n equals 6 to n equals 5, that's going down. So we're going to lose energy. So the overall should be negative. So this should be positive when all is said and done. So we're gonna have n equals, so the n equals 5 is going to be this one. So this is going to be 2. So the second one you go to, which is lower, and this is going to be 1. So the final minus initial. And so here, we're going to plug in our values for n equals 5 and n equals 6. Okay, so then this becomes, you can continue over here to give it space, so this is going to be negative 2.18 times 10 to the negative 18 joules. And so this is going to be 5, so that's going to be 5 squared minus 1 over, and 1 is going to be 6, that's our first one, so 1 over 6 squared. So again, then this is going to be equal to, and then we just calculate this out. So we can calculate it out using our calculator. So we have negative, oops, hold on a second. So we have negative 2.18 times 10 to the negative 18 multiplied by, and then we'll have 1 divided by 25, which is 5 squared, minus 1 divided by 36, which is 6 squared, and then that's going to be equal to, and we get, that's going to give us a negative 2.664 times 10 to the negative 20 joules of energy. So that's the change in the energy of our electron. So remember also that the change in the energy, the negative change in the energy of the electron is equal to the energy of the photon. So if we take the negative of this, that's going to be equal to 2.664 times 10 to the negative 20 joules. So that's the energy of the photon emitted, okay? And notice it's positive because photons don't have negative energy. They can only have positive energy. Now, what the problem is asking for is what is the wavelength of this light emitted? So we got to go back to the problem or the equation that we've used before. So that's going to be the energy of the photon, photon is equal to hc over lambda. So Planck's constant times speed light divided by wavelength. So if we solve this, we have this part, which is there. So we solve this for lambda. So lambda is going to be h equal to hc over the energy of the photon. So if we put this up, so this is going to be 6.626 times 10 to the negative 34. 34. And again, this is joule seconds, multiplied by C, which is going to be, now if we remember this, the joule seconds is actually kilograms times meters squared over second squared times seconds. Okay, and then the speed of light is going to be 3.00 times 10 to the 8 meters per second divided by, and then the energy of the photon, which we have here, which is going to be 2.664 times 10 to the negative 20 joules. So this is joules. So that's going to cancel out. So again, we have meters per second. So this is going to cancel out. So we have that canceling out with that. So joules cancel out with joules. Seconds are going to cancel out with seconds. And we have meters left over. So if we calculate this out, so we take this number, so we're going to take 6.626 times 10 to the negative 34 times 3.00 times 10 to the 8 divided by that, this number here, equals, and we get, so this is going to be equal to 0.0, how many zeros do we have? 1, 2, 3, 4, 5, 0, 0, 0, 0, 0, 7, 4, 6. So this is going to be in meters, and if we multiply by this by the nanometers, if we convert this to nanometers, it'll be 10 to the negative 9 meters over 1 nanometers. Meters cancels out, and if we divide this, so divide by 1 times 10 to the negative 9 equals, and that's going to give us, make sure I double check, yep, so that's going to give us 7,460 nanometers. So let's check our sig figs. We have 3 sig figs here. These are exact, so should we have 3 sig figs? We'll have 3 sig figs here. And so we have, so the 3 sig figs is the way to go. So we have our 3 sig figs. So that would be the answer in nanometers. I hope that's clear for that problem. The next problem is exactly the same, except instead of finding the wavelength, they give us the wavelength, and we need to find the missing part here. So the way we're going to do this, if I grab a new marker. So they give us the wavelength, so we need to go and get the energy of the photon that was released. So taking the wavelength, we'll have 9.38 or 93.8 nanometers. Okay. Actually, I'll finish this in the next video because I don't think I'll have time in this one. So please watch the next video. I'll see you in a few.